Ever think about how these huge software applications get built to be, uh, scalable and easy to maintain? And secure, too, of course.
Mm.
It's kind of like if you were building a skyscraper, you wouldn't just uh, start stacking bricks, right?
No, definitely not. You'd need a solid blueprint, a plan to make sure that building could handle what it's meant for and, stay safe and also be adaptable in the future.
Exactly. And that's where software architecture patterns come in. They're like blueprints for, well, for building robust software systems. So let's dive into some of the most popular patterns, the ones IT professionals are using these days.
Sounds good. Understanding these patterns is really helpful. It gives you a good foundation for understanding how modern software systems are actually designed and built.
Okay, so let's start with layered architecture. This one's all about, well, organizing your application into distinct layers, each one with a specific job to do. Think of it like a really well-organized kitchen.
I like that. Yeah, so you have your pantry, right, for storing all the ingredients. That's like your data layer. It holds all the raw data. And then you have your prep area where you process and combine the ingredients. That's like your business layer, handling the core logic.
And the stove and oven, where the actual cooking happens. I guess that would be the application layer. Executing the tasks
Yeah.
and coordinating everything between the layers.
Precisely. And finally, the beautifully plated dish, the one served to the diner, that's your presentation layer. It's the user interface,
Yeah.
what the user actually interacts with. That separation of concerns is one of the key benefits of layered architecture.
Right, right. Makes sense. So each layer can be developed and maintained kind of independently.
Yeah,
So
exactly.
that makes the system more scalable, right?
Yes,
And more flexible and easier to troubleshoot, I guess.
definitely. But like with anything, there's trade-offs, right?
Yeah, of course.
Adding too many layers, that can make the system complex, and then communication between those layers. Well, sometimes that creates performance bottlenecks. It's all about finding the sweet spot for your specific needs.
So it's about balance, right?
hmm
Where would we see layered architecture used in real applications?
Think e-commerce platforms, like Amazon, for example. Each layer handles a specific part of the shopping experience, like, browsing products, processing payments, even your banking app probably uses this pattern, separating your account information, the transaction processing, and the user interface that you use.
All right, moving on to client-server architecture. This one's about communication between a central server and multiple clients, like a busy library.
Oh, I like that. Imagine the library as the server, holding tons of books. That's your data, your resources. And you, the client, you request a specific book, right, by sending a request to the librarian.
Okay, so the server is the central hub. It's managing and providing access to all the resources, right? While the clients, they just request and use those services.
Exactly. This centralized approach has some big advantages, like easier maintenance, better security, and more control over the resources. But there are some downsides too, of course.
Like, what happens if the library closes? Unexpectedly.
Right.
Everyone's stuck without books.
Yeah,
Could that happen with a client-server system, too?
absolutely. That's the single point of failure risk. If the server crashes, well, all the clients, they lose access. That's why good systems have redundancy and backup mechanisms in place.
Makes sense. So, other than libraries, where else do we see this pattern being used?
Email services, like Gmail. The
Yeah.
server, it stores all the emails and manages the sending and receiving. And your email app on your phone or computer, that acts as the client. It lets you access and manage your messages.
All right, so let's talk about event-driven architecture. This one is all about reacting to, like, events or changes, like a chain reaction.
Ooh, like a domino effect. One domino falls, triggers the next one, and so on. In software, user actions, sensor readings, even internal system changes. Those can all be events that trigger a series of actions.
Okay, so instead of following a set path, the system is designed to be more responsive and adaptable to whatever happens.
Yeah, exactly. This makes event-driven architecture great for applications that need to process data in real time, like stock trading platforms or online gaming, where every action needs an immediate response.
It sounds super powerful,
Mhm.
but managing all those events in real time, that's got to get pretty complex.
Oh, for sure. Designing, debugging, and testing these event-driven systems. That can be really tricky. You're dealing with asynchronous events. They're all happening at the same time, making sure it's reliable and avoiding, unintended consequences. That's super important.
So it's not like a one-size-fits-all solution, right? What about real-world examples? Where else would we see this?
Real-time analytics dashboards, the ones that constantly update as new data comes in,
Hmm.
or fraud detection systems. They monitor transactions and trigger alerts if there's any suspicious activity. Even your car's anti-lock braking system, that uses event-driven architecture to react instantly and prevent wheel lockup.
Okay, onto microkernel architecture. This one kind of reminds me of building with Lego blocks.
Oh, interesting. Tell me more about that.
So you have your base plate, right? The foundation for your creation.
Uh-huh.
That's the core system in microkernel architecture. It provides all the essential functionalities. And then you have all these different Lego bricks, each one with its own shape and function that you can add or remove as you need.
Ah, I see it. So the Lego bricks, they represent those plug-in modules.
Huh.
They extend the core system with specialized features or customizations. Just like Lego, you can mix and match those plugins to, build a system for your specific needs.
Exactly. This modularity makes microkernel architecture incredibly flexible,
Yeah.
right, and scalable. You can easily add new features or update existing ones without, like, disrupting the core system.
And maintaining it's so easy. If one plugin needs fixing, you can do that without affecting um, any other parts of the system, like swapping out a faulty Lego brick without, you know, breaking down the whole thing.
Okay, so what's the catch? There's got to be some drawbacks to this approach, right?
Well, communication between the core system and all the plugins, that can get complicated, especially as the system grows. And since the core is so minimal, you might need to build some functionalities from scratch. That might be readily available in other more monolithic architectures.
So it's a trade-off between flexibility and, I guess, out-of-the-box features. Where would we see this pattern being used in real life?
Operating systems, like Windows or Mac OS. The core kernel handles all the basic tasks like memory management and process scheduling, while device drivers and other software components, they act like plugins, providing specific functionalities for different hardware and software.
All right, so now let's talk about microservices architecture. This one is kind of like having a team of specialized chefs instead of one head chef trying to, do everything.
Oh, I like that. Yeah. So instead of building this massive interconnected application, you break it down into smaller, independent services,
Yeah.
each one focused on a specific task or functionality. Like each chef has their own area of expertise.
So it's like building a network of collaborating services,
Yeah.
all working together seamlessly.
Yeah.
That must make development and scaling much easier.
Oh, absolutely. Teams can work on individual services without affecting the others. This speeds up development and deployment. And if one service gets super busy, you can just scale it up independently without impacting, the rest of the system.
Sounds amazing for developers.
Yeah.
But managing a whole network of independent services, that must have its own challenges, right?
You're right. Managing the communication and coordination between those services can get pretty complex, and there's a bigger risk of network congestion, as the number of services grows. And security is a big concern, too. You got to secure each service and how they interact.
So it's about carefully weighing the trade-offs, right? Where are microservices being used these days?
Look at Netflix. They've really embraced microservices to deliver, those seamless streaming experiences to millions of users. Each service handles a specific aspect like user authentication, content recommendations. This allows them to scale and adapt quickly.
So it's really powering a lot of the services we use every day.
That's amazing. Okay, now let's explore space-based architecture. Sometimes it's called cloud-based or grid-based architecture. This one seems to be all about tackling scalability head-on.
You can think of it like a massive shared memory space. It's accessed by lots of processing units, like a huge warehouse with tons of robots all working together to, fulfill orders. Each robot can access that shared inventory and work together to complete tasks efficiently. Okay, so instead of relying on one powerful server, you're distributing the workload across multiple nodes, like a well-coordinated team tackling a huge project.
Exactly. This distribution gives space-based architecture incredible scalability and performance capabilities. You can handle huge amounts of data and traffic just by adding more robots, to the warehouse.
But managing a distributed system like this, that's got to be complicated. What are some challenges you've run into, working with this architecture?
Well, designing and managing any distributed system is inherently more complex than a centralized one. You got to ensure data consistency across all the different nodes, and that's crucial. And communication between those distributed components, that can introduce latency, which, can impact performance if you don't manage it carefully.
So there are definitely things to consider. What are some real-world examples of this space-based architecture in action?
Think of those big e-commerce platforms like Amazon. They have to handle millions of transactions all at the same time. Or online gaming platforms. They need to keep millions of players connected, all interacting in real time. They all use space-based architecture to handle those massive workloads.
That's incredible. Okay, let's move on to master-slave architecture. Sometimes it's called primary-secondary architecture. This one sounds like a classic division of labor.
Ooh, like a construction site. You have your foreman, that's the master, and they assign tasks to the workers, the slaves. The foreman coordinates and oversees the whole project, while the workers, they do their assigned tasks and report back.
Okay, so the master component is the brains of the operation, making the decisions, delegating tasks.
Right.
While the slave components are the brawn,
Yeah.
carrying out the instructions.
Exactly. This division of labor makes the system really scalable. You can add more workers as you need to handle a bigger workload. And it also makes it more fault tolerant. If one worker isn't available, the foreman can just reassign the task to, another worker. That makes sure the project keeps going smoothly.
That's pretty clever. What happens if the foreman gets sick, though? Doesn't that put the whole project at risk? Could that happen if the master component in a master-slave system fails?
That's a really good point. The master component can definitely become a single point of failure if it's not designed properly.
Mhm.
Robust systems, they use failover mechanisms, so a backup master can take over if the primary one goes down.
That makes sense. So besides that potential single point of failure, are there any other trade-offs with this architecture?
Communication between the master and all the slaves, that can get a bit complicated
Oh.
and potentially impact performance, especially in those large systems. It's super important to optimize communication and minimize, the overhead for things to run smoothly.
So where do we typically see this master-slave architecture?
Database replication, that's where data is copied to multiple servers to ensure redundancy and high availability. If one database server fails, the system can just switch over to a replica. Or load balancing, where the master distributes incoming traffic across several servers to prevent any single server from getting overloaded.
Okay, let's dive into pipe filter architecture. This one reminds me of an assembly line, where each station performs a specific task on a product as it moves along.
I love that analogy. So imagine data flowing through a series of pipes, and each filter along the way, it performs a specific operation on that data, like, adding a component, refining a shape, or even just inspecting for quality.
So each filter has its own very defined responsibility, transforming or refining the data before, passing it on to the next filter in the line.
Precisely. This modularity is one of the key benefits of pipe filter architecture. You can easily add or remove filters to, change that data processing workflow. That makes it super adaptable to changing needs. And each filter is independent, so you can reuse them in different pipelines. That promotes code reusability.
It sounds really efficient and flexible. But are there any downsides to this?
Well, debugging can be a bit tricky. If you find an error in the final output, you got to, trace back through each filter to find the source. And all the filters have to agree on the data format. So there can be constraints in how that data is represented and transferred.
So it's powerful for data processing, but you need careful planning and design, right?
Yeah.
Where would we see this pipe filter architecture in real life?
Compilers. They process source code through a series of filters, each one doing things like lexical analysis, parsing, and code generation, or even image processing, where filters are used to apply, different effects to images like blurring, sharpening, color correction.
All right, let's wrap up this part with broker architecture. This one sounds like it involves lots of negotiation and coordination.
Think of a busy marketplace. You have your buyers and sellers, right? Each one looking for specific goods or services, but they don't interact directly. They use a broker to connect them, to facilitate the transactions and make sure communication is smooth.
Okay, so the broker's like the central hub,
Yeah.
receiving requests from clients and then routing them to the right servers for processing. It's like a really sophisticated matchmaking service for software components.
Exactly. This decoupling makes broker architecture very flexible and scalable. You can add or remove servers without, disrupting the whole system. And the broker, it makes things more fault tolerant by redirecting requests if one server fails.
Sounds pretty robust and reliable. But managing this broker component, That must have its own set of challenges, right?
You're right. Implementing a broker, you got to really think about the routing logic, load balancing, and all the security measures. If the broker itself fails, well, that can become a single point of failure if you don't design it with the right, failover mechanisms.
So it's a powerful pattern, but it needs careful planning and design, right?
Yeah.
Where would we typically see broker architecture being used?
Systems that integrate different enterprise applications like your CRMs, ERPs, and HR systems. The broker makes sure data exchange between all those, different systems goes smoothly. Or message brokers like RabbitMQ or Apache Kafka. That's where messages are exchanged between different applications or services.
Wow, it seems like broker architecture is really important for connecting all the parts of complex software systems. We've covered a lot in this part of our deep dive into software architecture patterns. From the well-organized kitchen of layered architecture to the bustling marketplace of broker architecture. We've seen how these patterns provide solutions for a whole range of challenges in software design.
It's been a great journey so far, and we're just getting started. In the next part, we're going to explore some more specialized patterns, the ones that tackle specific, unique challenges in software design.
Sounds good. So stay tuned for part 2. We'll be diving even deeper into the world of software architecture patterns. We'll see you there. Welcome back. We're continuing our deep dive into these software architecture patterns, exploring the blueprints that kind of shape the whole software world.
In this part, we're going to be focusing on some more specialized patterns, the ones that really tackle those unique challenges that come up in software design.
Okay, sounds intriguing. Let's start with Blackboard architecture. The name itself is pretty mysterious.
Yeah, think of a group of detectives, right? They're all huddled around a whiteboard. They're trying to piece together clues to solve this complex case. Each detective, they bring their own, expertise, analyzing the evidence, contributing their insights.
So it's like a collaborative problem-solving session, right?
Yeah.
Where everyone's kind of contributing their knowledge to that central board. How does that translate to the world of software?
So in Blackboard architecture, the central data store, that's the Blackboard, right? It holds all the information about the problem. And then you have all these specialized modules. They're like the detectives or the experts, and they can read and write to the Blackboard, adding new information, analyzing what's already there, and proposing solutions.
So each module contributes its own little piece of the puzzle, right?
Yeah.
Working indirectly through the Blackboard to solve the problem. What kind of situations would benefit from this pattern?
It's really good for problems that involve like uncertain or incomplete data, where the solution kind of emerges gradually, through collaboration. Imagine a speech recognition system. Different modules could analyze the audio signal, identify phonemes, match words, interpret the meaning, all contributing to the central Blackboard.
That's fascinating. So it's like a team effort, right, where the solution kind of evolves as more information becomes available. Are there any challenges with implementing this?
Well, managing that central Blackboard, that can get complex.
Yeah.
Especially when you have a lot of experts all, contributing data at the same time. Making sure the data is consistent and synchronized, that's crucial to avoid conflicts and make sure the solution is, sound.
So it's powerful, but you got to be careful with the data management and coordination, right?
Yes.
Let's move on to interpreter architecture. This one sounds like it's all about translation.
You got it. Imagine you're traveling to a new country and you don't speak the language. You need an interpreter, right? Someone to bridge that communication gap, translate in between your language and theirs.
So it's about understanding and acting on instructions that are given in a different language.
Yeah.
How does this apply to software?
So the interpreter pattern, it defines a grammatical representation for a specific language, right? And then provides an interpreter to process and execute the instructions written in that language.
So like a programming language interpreter, right?
Yeah.
That reads and executes code line by line.
Exactly. Think about Python or JavaScript. The interpreter takes that human readable code, right, and translates it into instructions that the computer can understand and execute.
That makes sense. What kind of applications would use this pattern?
If you need to create a domain-specific language or a scripting language to express some specific logic, this pattern is great. For example, a rule engine, right?
Yeah.
Used in a business application, it could use a specialized language to define those rules, and then an interpreter to evaluate those rules against the data.
So it's like creating a custom language, right? Just for a specific domain or task. What are some of the things to consider when you're implementing this interpreter architecture?
Interpreted languages, they sometimes sacrifice some performance compared to compiled languages because the code is, executed line by line. And debugging can be a bit tougher because you're dealing with that extra layer of interpretation.
So it's a trade-off, right, between flexibility and performance.
Yeah.
Let's move on to a classic pattern, one that's really widely used in web development. Model View Controller, or MVC.
MBC. It's like a really well-organized production line.
Yeah.
You have your raw materials. That's the model representing the data and logic of the application. And then you have your assembly process. That's the controller. It handles the, user input and updates the model.
And the finished product, ready for presentation. That's the view. It displays all the information to the user.
Exactly. Let's say you're browsing an online store, right? The product catalog, that's the model. Your actions, like adding items to your cart, that's handled by the controller. And those product pages you see, that's the view.
So it's about separating concerns, right?
Yeah.
Making the application more organized and easier to maintain.
Exactly. MVC is a great way to structure those, web applications. It makes the code more reusable, simplifies testing, and makes it easier to update the application without, creating a whole domino effect of changes.
But are there times when MVC might not be the best fit?
Well, while MVC is, powerful and popular, it can get really complex for very large applications, the ones with lots of views and controllers. And for simple applications, it might be a bit overkill. It might add unnecessary overhead.
So choosing the right architecture, it always depends on the needs of the specific project, right?
Yeah, absolutely.
Now let's talk about the repository pattern. This one sounds like it's all about storing valuable artifacts.
Oh, imagine a museum. It has this massive collection of artifacts. You, as a visitor, you wouldn't be allowed to just, directly access and handle those artifacts. Instead, you'd interact with a curator, someone who knows the collection really well.
Okay, so the curator is like the mediator, right, between the visitors and the collection. Retrieving and presenting those artifacts in a safe and organized way. How does that relate to software?
The repository pattern, it acts like that curator. It mediates between the domain logic of an application and the data access layer. It provides this nice, clean interface for retrieving and persisting data, hiding all the complexity of the underlying database or data store.
That sounds like a good way to keep the code clean and organized.
Absolutely. It promotes loose coupling between the different parts of the application, making the code easier to test and maintain. If you need to change the database or the data access logic, you only have to upgrade the repository. You don't have to touch the rest of the application.
It's like swapping out the museum storage system, right?
Yeah.
Without messing up the visitor experience. What are some of the considerations for implementing the repository pattern?
Well, for very simple applications, the ones that don't have a lot of data access needs, this pattern might be too much. It might add unnecessary complexity. And designing a generic repository that can handle all the different types of data access operations, that can be pretty challenging.
So it's a good pattern for applications that have complex data access needs. It provides that clean separation between data management and the application's core logic.
Yeah.
Let's move on to the strategy pattern. This one sounds like it's all about strategic planning.
Oh, imagine a general planning a military campaign. They have all these different strategies, right? Each one good for different terrains and enemy formations. The general chooses the best strategy based on the specific situation.
So it's about having a toolbox of different approaches, right? And picking the best one based on the context. How does this work in software?
The strategy pattern defines a whole family of algorithms, encapsulates each one, and makes them, interchangeable, like having different tools for different tasks. And you can swap them in and out as you need.
That sounds very flexible. Can you give an example of how this might be used?
Sure. Say you're building a navigation app. You might have different routing algorithms, one for the shortest distance, one for the fastest travel time, and one for avoiding tools. Using the strategy pattern, you can dynamically choose the most appropriate algorithm based on what the user wants.
So it's about offering options and letting the user or the system choose the best approach. What are some of the benefits of using the strategy pattern?
It makes your code more reusable. You can use the same algorithms in different parts of the application, or even in different applications entirely. And it makes testing easier because you can test each algorithm independently. And it's easy to add new algorithms without changing the existing code, that makes the application more extensible.
Sounds like a pretty elegant and powerful pattern. Are there any situations where the strategy pattern might not be the best choice?
Well, if you only have one or two, simple algorithms, the strategy pattern might be overkill. It could add unnecessary complexity. And if the algorithms are really similar, it might not be worth, the effort of separating them out.
So it's all about choosing the right tool for the job, right?
Ugh.
Considering the complexity of the algorithms and the need for flexibility and extensibility. That wraps up part two of our exploration of software architecture patterns. We've delved into some pretty fascinating patterns, each one addressing those unique challenges in software design. From the collaborative problem solving of Blackboard architecture to the strategic planning of the strategy pattern, we've seen how these blueprints can help us build more robust and adaptable software systems.
It's been a great journey so far, and we still have more to explore. In part three, we're going to wrap up our deep dive by discussing some key things to consider when choosing the right pattern for your project.
Awesome. So don't miss part three. We'll be tying everything together and give you some valuable insights for navigating the world of software architecture patterns. See you there.
All right, welcome back to the final part of our deep dive into software architecture patterns. We've really covered a lot, from the basic ones like layered architecture to the more specialized ones like the strategy pattern.
Yeah, we've seen how these patterns are they're like blueprints,
Hmm.
guiding developers in how to structure these complex systems and address all these recurring design challenges.
It's been really cool exploring all these patterns, but now comes the big question. How do you actually choose the right one for your project? I mean, it can feel pretty overwhelming, right? There's just so many options to think about. Oh, absolutely. There's no magic answer that works for everything, but there are some key things to keep in mind, things that can help you narrow down your choices and make a good decision.
Okay, so what are some of the most important factors, when you're choosing a software architecture pattern?
Well, the first thing is to really understand what your project needs. What are the specific requirements and constraints?
So things like, how big and complex the application is going to be, the performance requirements,
Yeah.
security needs, and even budget limitations. All those play a role.
Yeah, exactly. And don't forget about your team, their skills and experience. Choosing a pattern that your team is comfortable with, that's really important for success. It's not just about picking the newest or the fanciest pattern. It's about the one that really fits your team's strengths and the project's needs.
It's like choosing the right tools for a construction project. You wouldn't use a sledgehammer when all you need is a screwdriver, right?
Hmm.
So once you've figured out what your project needs, how do you actually go about evaluating the different patterns?
Well, you got to think about the strengths and weaknesses of each one, right? In relation to your specific requirements. Like, if scalability and fault tolerance are at the top of your list, then microservices architecture or space-based architecture, those might be good options to consider.
But if being easy to maintain and easy to develop are more important, then maybe layered architecture or MVC might be better.
Exactly. It's all about finding that perfect fit and realizing that every choice has trade-offs, right? There's no perfect pattern. It's
Yeah.
about understanding which compromises work best for your goals.
Are there any other things that could influence the decision?
Oh yeah, definitely. The type of data you're working with can also play a big role. For example, if you've got really complex data relationships and you need to make sure that data stays consistent, then the repository pattern could be a good choice.
And if you're working with a stream of data that needs to be processed in different stages, then the pipe filter pattern that might be the answer. It's really interesting how these patterns can be combined and adapted to create solutions for so many different situations.
Yeah, that's what's so great about software architecture. It's not about, rigidly following the rules. It's about being creative, applying these patterns, sometimes even, blending them together to come up with the best solution for your specific challenges.
So it's more of an art than a science then.
You could say that, yeah. It's about finding that balance between, having structure and having flexibility,
Yeah.
using these patterns as guides, right? Not as strict rules.
And in the end, the goal is to create software that's strong, and easy to maintain and adaptable.
Yeah.
Software that can keep up with the changing needs of its users.
Exactly. Software architecture, it's really the foundation, for building successful software.
Well, this deep dive into software architecture patterns it's been amazing. I've learned so much.
It's been great exploring all this with you and with our listeners. Hopefully everyone feels, a little more equipped to navigate this world.
I'm sure they do. We've covered a lot of patterns, each one with its own strengths and weaknesses, and we've talked about the key things to think about when you're choosing the right pattern for your project.
And remember, there's no one right answer. It's about really evaluating your needs, understanding what your options are, and then making smart decisions.
And don't be afraid to experiment. Software architecture, it's always changing.
Oh, absolutely. You got to keep learning, explore new patterns, and adapt to, those changing requirements. That's how you succeed in this field.
And that wraps up our deep dive into software architecture patterns. We hope you found it, insightful and helpful.
And if you enjoy this deep dive, make sure you subscribe to our channel for more Topictrick episodes. We take these complex tech topics and we break them down in a way that's, easy to understand. We'll see you next time.